In today's video, we are looking at linear models. So one of the first things that we did in this class is we looked at modeling physical situations, and we stopped at just writing the model. What we're going to do today is we're going to build on that. We're going to write the model, but then we are also going to solve and come up with our final solution using some initial values. Mostly we're going to be looking at growth and decay of the following types. Maybe it's bacteria or a population. We're going to look at Newton's law of cooling and some radioactive decay and so on and so forth. So the general equation, as you can see to the right, is going to be dx dt is equal to k times x, right? And so if you remember, dx dt is our rate of change of whatever it is we're looking at, a population, a bacteria, so on and so forth. And we said it's proportional to whatever the value is at that time. And then we're going to have some initial condition. So this is our initial value. Okay, so I should have said this at the beginning. You are going to need a calculator. So if you don't have a calculator, I would grab one. Example 1, a culture has N0 bacteria initially. At t equals 1 hour, there are 2.5 N0 bacteria. Assuming the rate of growth is proportional to the number of bacteria present, determine the time necessary for the bacteria to quintuple. So let's start with what we know. We know the number of bacteria at time 0 is N0. We know the number of bacteria after 1 hour is 5/2 times N0. And we know that the rate of growth of the bacteria, which is our derivative, is equal to k times n. Okay, so this is everything that we know. And from here, of course, we're going to solve. If we look at our differential equation, we notice that that equation is separable. So we're going to solve by separation. So we get dn over n is equal to k dt. If we integrate, we have the natural log of n is equal to kt plus c. If I call this c1, I'm then going to get n is equal to c2 e to the kt. Now is where we can use some of those initial conditions. So I'm going to start with this first one. So using our solution we came up with, we get N0 is equal to C2 e to the 0. So C2 is N0. So now we have N is equal to N0 e to the KT. So then we're going to use our other condition, this second one. So we get 5/2 N0 is equal to N0 e to the 1K. So if we divide out those n naughts, then we're going to get k is equal to the natural log of 5/2. So where that leads us then. Now our equation is n of t is equal to N0 e to the natural log of 5/2 t. Okay, now finally we can answer the question that we were asked. Determine the time necessary for the bacteria to quintuple. So we have 5 N0 is equal to N0 e to the natural log of 5/2 t. So we separate those out. Now we're going to have to look, how can we simplify this? Well, another way we can express that, this is the same as e to the natural log of 5/2 to the t power. Right? And then this e to the natural log of 5/2 is just 5/2 to the t. Okay, so where we are now then, we have 5 is equal to 5/2 to the t. So you can put this in log form. You can take the natural log of both sides, whatever you prefer. So I end up with t is equal to the natural log of 5 over the natural log of 5/2, which is about 1.76 hours. Now, one thing that I should have mentioned earlier that hopefully you did a mental check, when you got this value of k, you should have asked yourself, does that make sense? What we know is that natural log of 5/2 is positive, so this is a growth situation. So yes, that would make sense. To remind you, we're going to write this down. For a decay situation, K is going to be less than 0. And how do you know if we're taking a look at natural log? Well, natural log of A will be greater than 0 if A is greater than 1. And if A is between 1 and 0, then our natural log will be negative. So that was our first example. You've very likely seen something very similar to that before. So let's take a look at another one on the next page. A radioactive substance decays so that after 10 years, 1.3% has decayed. Find the half-life, assuming all the usual things that we assume. Okay, so first thing, we know the rate at which the substance is decaying is proportional to the amount at a certain time. And we're going to say the amount at time 0 is A naught. This equation is separable. We already solved it on the previous page, so that you know that A of t is going to be A naught e to the kt. So we solved that in the previous example. You can just memorize that if you want. So if you just want to memorize so that you don't have to solve every time, that's perfectly fine. If you don't want to, that's fine too. So now let's go to the information that we actually have. After 10 years, 1.3% has decayed. So what that means is A of 10, if 1.3% has decayed, then 0.987 of the initial amount remains. Okay, so at this point, we're going to take a pause and see where are we, what do we need? At this point, we need K, which is why we have this initial condition. So that's where we're going to go next. I have 0.987 times the initial amount is equal to the initial amount e to the 10k. So we can divide out that initial amount and take a natural log. When we do, we get the natural log of 0.987 is equal to 10k. So our k is equal to natural log of 0.987 over 10. Now, like we did before, we need to think, does this make sense? Is this a correct value of k? Natural log, if the argument is less than 1, that natural log is going to be negative. So because k is negative, that makes sense in terms of a decay situation. So right now, what we have for our equation is we have A of t is equal to A naught e to the natural log of 0.987 over 10t. Okay, so finally, now we can go to what we were being asked, find the half-life. So we want to know how much time does it take for half of the amount to remain. So we're going to have 1/2 A naught is equal to A naught e to the natural log of 0.987 over 10 times t. And of course, you're going to go and solve this. We're not going to because you've seen many of these examples before, but that is the way you would approach this problem. Okay, so next thing that we are going to look at is we're going to take a look at Newton's law of cooling. So here's the idea with Newton's law of cooling. You have a cooling body. The temperature of which we say is T of B. So this is our cooling body. And it is in some surrounding medium. And the temperature of that we say is T of M. So we say the rate at which the body cools, so this is the rate at which the body cools, is proportional to the difference in the temperature between the body and the surrounding medium. So that is Newton's law of cooling. So next thing we're going to do is, of course, an example with Newton's law of cooling. A cake is taken out of an oven with a temperature of 300 degrees Fahrenheit. 3 minutes later, its temperature is 200 degrees Fahrenheit. How long until its temperature is 85? And I'm telling us that the temperature in the room is 70 degrees Fahrenheit. So let's start with an equation and the conditions we have. So we know the rate at which this cake is cooling is proportional to the difference between the current temperature of the cake and the temperature of the room, which is 70. We know at time 0 that our cake is at 300 degrees. And we know that after 3 minutes, our cake is at 200 degrees Fahrenheit. So this is all of the information that we've been given, and we want to know the time when the temperature is 85. Okay, so looking back at our differential equation, of course, this is separable. So we're going to separate and then integrate. So we have dt over t subtract 70 is equal to k dt. So we integrate, which gives us the natural log of t subtract 70 is equal to kt add c. So if we apply an e, we get t subtract 70 is equal to c2e to the kt. So then t of t is c2e to the kt add 70. And so this will give the temperature of the cake at time little t. So that is our general solution. Now, of course, we have two things that we need to find. We need to find C2 and we need to find K. So we're going to go to our condition T of 0 equals 300. So that gives us 300 is equal to C2 add 70. So our C2 is 230. Then if we go to our condition that T of 3 is equal to 200, we're going to get 200 is equal to 230 e to the 3k add 70. So we end up with 130 is equal to 230 e to the 3k. So this, when we divide by 230, we get 13/23 is equal to e to the 3k. So our k then is going to be natural log of 13/23 all over 3. Again, make sure this makes sense. Does this make sense? The first thing we should look at is, what do we know about this natural log? Well, because the argument is less than 1, this natural log is going to be negative. Does that make sense? Well, yes, it makes sense in this case because the cake is cooling. The temperature is going down. It's decreasing. Okay, so where does this leave us currently? So now our equation becomes T of t is equal to 230 e to the natural log of 13/23 all over 3t add 70. Okay, so now finally we can actually answer the question. We want to know what the time is going to be, or how much time it will take for the cake to get to 85 degrees. So we're going to set all of that equal to 85. Okay, so of course you can tell we're going to need to get this e alone. So if I subtract 70 and I divide by 85, I'm going to get 3/46 is equal to e to the natural log of 13/23 over 3t. Okay, so now at this point, really ideally what we want is we want e to just the natural log. So what we're going to have to do is we're going to have to rewrite that right side a little bit. And so what I'm going to do is I'm going to write this as e to the power natural log of 13/23 to the power t over 3. So what I did was pull out this t over 3. And so you should confirm, don't just trust me, that this quantity is the same as this one above. Okay, so then where does that leave us? That leaves us with 3/46 is equal to 13/23 to the power t over 3. Okay, we might be taking a look at this now and being like, where do I go from here? So at this point, either you can put this in log form or take the natural log of both sides. So if you do that, you're going to get natural log of 3/46 is equal to t over 3 times the natural log of 13/23. So we're almost there. Our t is going to end up being 3 times the natural log of 3/46 over the natural log of 13/23. And if you're like me, you look at that and you're like, I really have no idea what that quantity is. So I will tell you that's about 14.35 minutes. So it will take about 14.35 minutes for the cake to reach 85 degrees. Okay, we've got one more application. These examples we've been doing are all ones that we covered at the beginning of class, at the beginning of this course where we looked at general modeling. The last one that was new to us, if you remember, is mixing in salt solutions. So that is the last application we will take a look at in this video. Okay, so here it is. A large cylindrical tank has 300 gallons of water in which 50 pounds of salt is dissolved. A mixture with 2 pounds of salt per gallon is entering the tank at a rate of 3 gallons per minute. At the same time, liquid is leaving the tank at a rate of 2 gallons per minute. So in part A, we need to find an equation to determine the amount of salt in the tank at time t. And in part B, we need to find how much salt is present after 1 hour. Okay, so I will tell you I am a very visual person. So for me, I have to start with a picture so that I see what is going on. So first thing we are told is we have a cylindrical tank. And in that tank, we know that we have 300 gallons of water and we have 50 pounds of salt dissolved. Then we know that we have a mixture that is coming in. So that mixture has 2 pounds of salt per gallon, and it's coming in at 3 gallons per minute. Then we know that we have a hole in the bottom and we have some solution that is leaving, and it is leaving at 2 gallons per minute. Okay, so that is a picture of what's going on. So the question is, where do we go from here? If we're taking a look at part A, writing an equation, what's going on is the rate at which the amount of salt is changing. So A is the amount of salt, right? We're told amount of salt at time t. So the rate at which the amount of salt is changing is the difference between what's entering and what's leaving. So R1 is the rate that we're entering at, and R2 is the rate at which the salt is leaving. Okay, so I'm going to pause there. So what we're doing is we're finding how much salt is coming in, how much salt is leaving. So let's start with R1 because R1 is consistent. R1, the rate at which the salt is entering. Well, we know that we have a solution that's entering at 3 gallons per minute. And we know that the solution has 2 pounds of salt per gallon, which gives us then there are 6 pounds of salt entering every minute. Okay, so if we look at this, we took a rate and we multiplied by a concentration. So R2, the rate at which this solution is leaving. The rate we know is 2 gallons per minute. Now we need to figure out the concentration. Okay, so the concentration of what is leaving is the same as the concentration of what's in the tank. Well, what's in the tank at any point is A pounds. That's what A represents. A is the amount of salt. So if there are A pounds of salt in here, then the concentration of what's coming out is also going to have A pounds in it. Okay, so looking above, we need A pounds per gallon. So we need to figure out how many gallons are in the tank at any time. Well, we know we start with 300 gallons. If there are 3 entering, and 2 leaving, every minute, we're going to have 1 more gallon. So after every minute t, we're going to have 1 more gallon. So simplifying this gives us 2A over 300 plus t. And again, we're going to notice this gives us pounds per minute, which matches the units of what we have above. Okay, so where does this bring us then to an equation? I'm going to start on the left side, or I'm going to continue on the left side. So I have dA dt is equal to 6 subtract 2a over 300 plus t. Okay, and then is there anything else that we haven't used? Well, we still need an initial condition. We know at time 0, there are 50 pounds of salt in the tank. Okay, so now that we finally have our model, it's time to actually solve this. So that's where we're going here. First thing that you're going to notice is this is not separable. So it might be helpful if we rewrite this in a different order. So we have dA dt is equal to, not equal, add 2a over 300 plus t is equal to 6. So hopefully if you write it in this way, we recognize that this equation is linear. To solve a linear equation, we need to find our integrating factor, which is going to be e to the integral of 2 over 300 plus t dt, which is e to the power 2 natural log of 300 plus t, which is really 300 add t quantity squared. Okay, so if we multiply our equation by that, we're going to get 300 add t squared dA dt, add 300 add t squared times 2a over 300 plus t equals 6 times 300 plus t quantity squared. Okay, if we did things correctly, on the left side, we should end up with the derivative of 300 add t squared multiplied by a. Don't just trust that. Make sure that that is actually the case. And hopefully you can do a quick mental check to show that yes, the left side does in fact end up as the derivative of that product. On the right side, we have 6 multiplied by 300 add t quantity squared. So we're going to integrate. We get 300 add t squared multiplied by a is equal to 2 add 300 add t to the third add c. So our a of t then is 2 multiplied by 300 add t add c times 300 add t to the negative second. So this will give us the amount of salt in the tank at time t. So then if we use our condition a of 0 equals 50, that gives us 50 is equal to 2 times 300 add c times 300 to the negative second. I've done this calculation for you, and I will tell you c ends up being negative 49,500,000. So part A, finally our answer is a of t is equal to 2 multiplied by 300 add t, subtract 49,500,000 times 300 add t to the negative second. Okay, so then finally part B asks us how much salt is present after an hour, so after 60 minutes. And again, I've done that calculation. I will tell you it ends up being about 338.06 pounds. Okay, that was our video for today. Hopefully this was nice to return to something that we did at the beginning of the course. We wrote the models and now we actually know how to solve some of them, which is pretty cool. So until next time, thank you for watching.